We are jumping straight into a paper today titled, read it back, Pre-trained MLLMs are zero-shot reward models for text-to-image generation.
Yeah, this is by Runwei Huang and a joint team of researchers from HKU, ByteDance Seed, and Peking University.
And welcome back to AI Paper Slut. By the way, I want to give you the core insight right out of the gate today. So if you're a machine learning engineer working on generative vision, you know the biggest bottleneck in text-to-image reinforcement learning.
Oh, designing the reward model. It is a complete nightmare right now.
Exactly. RLHF, getting humans to rank images, it costs a fortune and it just doesn't scale. But if you take the cheap route and prompt an MLLM for like a 1 to 10 score, the gradient is incredibly noisy.
Right, which brings us to the breakthrough here. The authors introduced something called SpectraReward.
And it is entirely training free. You just take a frozen, pre-trained MLLM, condition it on the generated image, and do a single teacher force forward pass on the original text prompt.
The reward is literally just the average token level log likelihood.
Yeah, and it gets even crazier. They introduced Self-SpectraReward for unified multimodal models, or UMMs, like Bagel. The model basically uses its own understanding branch to critique its own generation branch.
Right, it's a closed loop, and this setup matches or outright beats external reward models that are like 30 times its size.
Which proves reward policy alignment matters way more than just throwing parameters at a problem.
For sure. To put this in perspective for the teams out there fine-tuning diffusion or autoregressive models, this changes the whole resource calculation.
It really does. I mean, it's off the shelf, right?
Yeah, highly elegant. It reuses the foundational image-text alignment these models already learned during their massive pre-training runs. You don't need a single preference label. You don't need to fine-tune a specialized judge. Nothing.
And you totally bypass those awful, complex question decomposition pipelines. It's a mathematically clean fix to a problem that's been hard-capping image models for the past year.
Exactly. It's wildly compute efficient.
So let's unpack the mechanics of this. Because to really get why checking token probabilities is such a game changer, we have to talk about why current reward models are failing us.
Oh, they are definitely failing.
Right. Like, you and I know RL is amazing for post-training. When you want perfect compositional fidelity or strict instruction following, RL is your tool.
But the RL optimizer is blind. That's the catch.
Exactly. It is completely at the mercy of the reward model to tell it which direction is up. The reward model sets the absolute performance ceiling.
Because the optimizer can only climb the specific hill that the reward function defines. And historically, we just defaulted to RLHF, reinforcement learning from human feedback.
Which is so painful for dense visual composition.
Right. If you ask a human to verify if an image perfectly matches a super complex prompt, they just get fatigued. And worse, they introduce massive bias.
Oh yeah, the aesthetic bias.
Exactly. Humans love shiny things. Data shows human raters get distracted by beautiful lighting or, incredible high-res textures.
They'll give a high rating even if the model completely hallucinated the wrong number of objects or messed up the spatial layout.
Yeah, they just see a pretty picture and click 5 stars.
So because humans are expensive and easily distracted, the industry pivoted. We automated the human away by using MLLMs as zero-shot judges.
But the two ways we do that right now are fundamentally broken.
Totally. The first is Scalar Scoring. This is, it's like handing a complex painting to a lazy, pretentious art critic, right? And saying, rate this 1 to 10.
And the critic just spits out a 7.
Right. You get a number, but zero granular feedback. Was the background wrong? Did it miss an object? Were the colors off?
You have no idea. It's incredibly sensitive to judge calibration and just full of noise.
So that lack of a localized gradient drove the field to the second paradigm, which is VQA decomposition, or visual question answering.
Which tries to solve the granularity issue. You pass the prompt through an LLM to break it down into this rigid checklist.
Like, is there a cat? Is the cat orange? Is it sitting on a wooden table?
Right. And then you feed those atomic questions into a VQA model and aggregate the confidence scores.
Which, sounds logical, but in practice, you're just handing that same lazy critic a 50-point checklist. It introduces a ridiculous amount of engineering complexity.
So a massive pipeline, a prompt parser, a question generator, a vision language evaluator.
Yeah, and the whole thing gets bottlenecked by the decomposer.
Right.
If it hallucinates a question, your reward model is totally broken. But this actually brings me to my main pushback on the new paper.
Yeah, okay, let's hear it.
The authors are asking an MLLM to look at an image and basically read the prompt back. But isn't that exactly what contrastive models like CLP have been doing for years? Why is an autoregressive MLLM suddenly better here?
Okay. So contrastive models like CLAP operate globally. CLAP embeds the whole image into one vector, the whole prompt to another, and just gives you the cosine similarity.
So just one overarching score.
Exactly. If your prompt has 8 specific constraints and the generator nails 7 but completely drops the 8th, CLAP just gives you a vaguely lower global score.
It doesn't tell the RL optimizer which of the 8 things actually failed.
Right, it's not localized at all. But an autoregressive MLLM is different because it predicts text sequentially, token by token.
So by running that teacher-forced forward pass, SpectraReward gets a dense token-by-token feedback signal.
Exactly.
Just for the engineers listening who might be a little rusty, a teacher-forced forward pass means we aren't letting the model free run and hallucinate its own caption, right?
Right, we are clamping it down.
We give it the generated image as a condition, feed it the exact text prompt word by word, and ask, what is your mathematical probability of generating this specific next word?
That's the exact mechanism. You force the model to evaluate the likelihood of the ground truth prompt.
And the final reward is just the mean prompt token log likelihood.
Yes. Averaging the log probability of each token conditioned on the image and the previous tokens, the authors call this localized feedback the semantic spectrum.
Semantic spectra, I love that.
It's what lets the RL algorithm penalize missing attributes precisely where they occur in the text string, instead of just downgrading everything.
The visual examples they put in the paper for this are fantastic. Like, imagine your prompt is, 2 kittens sit in a blue box.
Okay.
If the model generates an image of 5 kittens in a blue box, the semantic spectrum reacts perfectly. When the MLLM hits the word kittens, the log likelihood stays high because, well, there are kittens.
Right, kittens are present.
Same for blue and box. But when it evaluates that specific token for 2, the probability absolutely tanks.
Because the visual evidence clearly contradicts that specific count. It creates a localized gradient pointing directly at the failure.
Yeah, and they showed another one with attribute mismatch. If you prompt for a guitar and it draws a chair, the likelihood is stable until it hits the exact word guitar, and then it drops off a cliff.
So the RL algorithm knows exactly which semantic concept needs adjusting in the latent space.
It's remarkably clean. But if I'm deploying this, my first technical concern is the language prior.
The baseline probabilities.
Yeah. Autoregressive models are language models first. So certain words naturally have higher likelihoods, regardless of the image.
Right, stop words.
Exactly. Words like the, and, or in will always score high just because of English syntax. So shouldn't we subtract a text-only likelihood term?
Like a point-wise mutual information or PMI normalization?
Yeah, PMI normalization. Otherwise, prompts with tons of common stop words will just artificially score higher than dense descriptive ones.
It's a standard hurdle, and the authors definitely analyzed it. But they actually found TMI normalization was entirely unnecessary.
Wait, really? Why?
It comes down to the specific RL algorithms used here. They rely on group relative RL methods, specifically AWM or advantage weighted matching.
Oh, okay. That makes sense. Because you aren't just judging one image in a vacuum. You're generating a whole batch for the same prompt.
Exactly. You sample, say, 8 different image variations, all conditioned on that exact same text. Within that specific group, the text-only likelihood is a static constant.
Oh, wow. So the language bias for the word the is identical across all 8 images.
Right. And AWM calculates the group relative advantage, so it looks at how much better image A is compared to the batch mean.
And when you subtract the mean, that constant text prior just beautifully cancels itself out mathematically.
Completely cancels out. The relative differences are driven purely by the visual conditioning.
That is some brilliant engineering. You get the pure semantic alignment without the computational nightmare of running a separate baseline calculation.
Yeah, it's extremely elegant.
So SpectraReward is great with an external MLLM API, but here's where the paper takes a wild turn. Self-SpectraReward.
Oh, this is the best part of the paper.
They realized if you're training a unified multimodal model, a UMM, you don't even need an external judge. You already have an MLLM built into the architecture.
Right, UMMs represent a massive shift. They use Bagel as the primary testbed here. Unlike isolated diffusion models, UMMs integrate visual understanding and generation into one cohesive framework.
So Self-SpectraReward basically has the policy model's own understanding branch serve as the reward model for its own generation branch. It's literally marking its own homework. It's a totally closed loop system, 0 external models. But I have to say, pitching this to an AI safety team sounds like a disaster.
Why do you say that?
Well, if a model has a fundamental blind spot, say it just can't draw a bicycle properly, won't its understanding branch have that exact same blind spot when trying to recognize a bicycle?
Oh, I see where you're going.
How does this not just spiral into a catastrophic feedback loop of its own biases?
It's a totally valid intuition, but it ignores what the paper calls a structural advantage.
Okay, what does that mean?
In a UMM, the understanding and generation branches aren't isolated silos. They share the exact same tokenizer, the same vision encoder, and crucially, they were trained on the exact same massive pre-training distribution.
So they speak the identical internal language?
Yes. This shared architecture creates perfect reward policy alignment. The latent representations the understanding branch uses to read an image perfectly map to the latent distribution the generation branch samples from.
So when the internal judge flags a token as unlikely, that gradient is perfectly tailored to the generator's parameters.
Exactly. Zero translation loss. It turns out having a judge that intimately understands your specific latent space is vastly more valuable than an objectively smarter external judge that uses totally different embeddings.
Wow. Which perfectly tees up the empirical surprises in this paper, because the data absolutely backs up that structural advantage, and it delivers some huge shocks to the industry's scaling laws.
Yeah, the assumption that bigger is always better gets totally dismantled here.
All right, the prevailing narrative is always just use a larger model for zero-shot supervision. But they tested 9 different MLLMs across 4 major families: Gemma 3, Intern VL 3.5, Qwen 3VL, ranging from small 4 billion models up to 235 billion parameter behemoths.
And they ran them on 5 distinct benchmarks: Genevil, TIFF-bench, DPG-bench, Genevil 2, and WISE.
Testing everything from spatial relations to object counts, and the first huge shock: scaling the reward model is strictly non-monotonic.
It does not just go up and to the right.
Exactly. Within the Qwen 3VL family, moving from the 8 billion model to the 30 billion model definitely improved the generation metrics. But when they scaled all the way up to the colossal 235 billion parameter model,
Performance actually dropped.
which is wild, the generator trained by a 30B model outperformed the one trained by the 235B model. Why would a frontier class model be a worse judge?
The hypothesis is that these giant models over-index on complex reasoning and conversational instruction following. Their latent spaces are optimized for, like, solving advanced math puzzles from a screenshot or writing code.
Right.
But SpectraReward doesn't need abstract logic. It relies on core foundational image captioning. Are the raw pixels matching the basic nouns and verbs?
So that foundational ability just saturates it around 30 billion parameters.
Exactly. Pushing past that introduces abstract reasoning noise, pulling focus away from pure visual semantic alignment.
That makes total sense, and it leads into the second surprise about how these judges should be trained. For the Gemma 3 to 12B architecture, they tested both the base pre-trained version and the instruction-tuned version.
And the base pre-trained model consistently beat the instruct model every time.
Which perfectly aligns with what you just said about the 30B ceiling.
Yeah.
Think about what pre-training actually is. It's massive scale image captioning.
Right. Next token prediction on billions of scraped image text pairs.
Which is almost identically what SpectraReward is asking the model to do during that teacher force pass.
But instruction tuning fundamentally shifts the output distribution. It trains the model to be a conversational assistant.
Yeah, it starts outputting filler or internal thought tags before getting to the actual visual semantics.
Exactly. For a strict log likelihood calculation, instruct tuning actively misaligns the internal probabilities. The raw pre-training data is just a much purer signal.
This totally flips the meta. You don't need to burn your budget renting a painfully slow 200 billion parameter API for your RL judge. A 30 billion base model gives you better, less noisy gradients.
And then there's the biggest shock in the paper: the David versus Goliath moment with Self-SpectraReward.
Oh, the internal bagel benchmarks.
Yes. When they used Bagel's internal 7 billion parameter understanding branch to grade its own generation branch.
It matched or outperformed external models 30 times its size. A 7 billion internal branch beat the 235 billion external Qwen model.
A perfectly aligned internal model absolutely crushes a massive disconnected external judge.
That is just stunning validation for the reward policy alignment theory. The distributional match is just a cleaner optimization path than brute forcing with raw compute.
The implications for open source are huge. It proves unified, relatively small models can autonomously self-improve without needing massive GPU clusters for supervision.
Okay, for the practitioners listening who want to implement this, the paper has some hyper-specific engineering ablations that make or break this in production. First, the RL algorithm. They tested AWM, FlowGRPO, and diffusion NFT.
And AWM was the definitive winner.
Because of that group relative approach we talked about earlier.
Right, it smooths out the variance of the autoregressive probabilities way better than the others in this specific framework.
Now, here's a fascinating technical hack regarding the EOS token, the end-of-sequence token.
Oh, this is such a cool detail.
Yeah, if you include the EOS token in the mean log likelihood calculation, the model's performance drops significantly.
Right, and you have to understand how an MLLM processes visual captions to get why.
Explain that, because it seems counterintuitive.
So text has a definitive grammatical end, right? A period. But a visual scene does not. When an MLLM looks at an image, it's nearly impossible for it to predict exactly when a descriptive caption should terminate.
Because a dog in a park could always just be described as a dog in a park on a sunny day chasing a ball.
Exactly. The visual details could technically go on forever. So the model always suppresses the probability mass of the EOS token. It's never fully confident the description is done.
So if you include that artificially low, highly uncertain EOS probability in your average, it just tanks the overall score and adds massive noise.
Yeah. So the authors simply chopped the EOS token off the calculation and instantly saw a boost on Genival and TIFF bench. It's a classic, brilliant ML engineering fix.
Just born from really understanding the difference between visual and text embeddings. And for anyone training a unified model like Bagel, there's another architectural hack. Bagel uses two types of visual features.
VIT features for semantic understanding and VAE features for raw pixel generation.
Right. And when calculating self-SpectraReward, if you feed both the VIT and the VAE features into the understanding branch simultaneously, you get much better optimization than using VIT alone.
Because you're giving the internal judge the absolute complete visual context of the generation process. It maximizes that structural advantage.
It totally reinforces the closed loop. But as robust as this is, we do need to highlight the hard technical limitations here. SpectraReward isn't magic.
No, definitely not. The reward model still sets the absolute structural ceiling.
Right. If the MLLM judge is fundamentally blind to a specific nuance, it cannot provide a gradient to improve it. Like if it doesn't understand advanced physics visually.
Say how light accurately refracts through a glass prism.
Yeah. The generator can never learn to draw physically accurate refractions using this method, no matter how long you train it.
Exactly. When the generator outputs break-in, unphysical refraction, the judge won't recognize the error. For the tokens describing refraction, the semantic spectrum will just be flat.
Zero useful gradient signal. The policy model can only ever become as good as the judge's inherent comprehension.
Which is an important constraint to keep in mind.
So to synthesize this for everyone listening, this paper proves you can extract a state-of-the-art reward signal for text-to-image RL just by checking the token-level log likelihood of a frozen MLLM.
No more noisy scalar scoring, no more massive VQA engineering nightmares.
Zero expensive human preference data. Plus, if you're building a UMM, the Self-SpectraReward framework proves that pure alignment lets a 7 billion parameter internal branch out-supervise a 200 billion parameter behemoth.
You can achieve incredible compositional generation locally, just through architectural self-critique.
It's a total paradigm shift. We're moving from how do we get more human data to how do we mathematically extract the alignment already baked into the pre-training weights.
And honestly, the success of this leaves us with a truly provocative question about the future of unified models.
Oh, I know where you're going with this. What's the next step?
Well, if UMMs can already self-improve their generation purely by critiquing themselves with their understanding branch, what happens when we apply RL to the understanding branch at the exact same time?
Oh, man. So as the generation branch gets better, it starts producing highly complex adversarial visual edge cases.
Right. And those edge cases get fed right back in to challenge and mathematically improve the understanding branch's visual comprehension.
Are we just approaching an autonomous flywheel where synthetic self-play entirely replaces human-curated alignment data sets?
It's totally possible. It's the AI equivalent of playing chess against yourself millions of times until you're a grandmaster, but applied to generative vision.
It really makes you wonder if our reliance on massive human annotation farms is just a temporary crutch. Maybe the answer to AI alignment isn't bringing in thousands of humans to read the outputs.
Maybe the answer is just building the architecture that lets the machine finally read its own outputs.
I think that's the perfect place to leave it. That does it for our breakdown of Read It Back. Here on AI Paper Slot, we will definitely keep tracking these architectural shifts as they happen. Catch you on the next one.